how we do merging on GPUs and CUDA. In CPUs, merging typically happens using a merge function. So, for example, if you have merge sort, you would have a merge function in merge sort, using which you would do sorting in merge sort, right? But then you cannot use the same logic that you use in CPUs because CPUs use a sequential algorithm. So for GPUs, we'll be discussing a parallelized version of the merge function. So the problem is we'll be trying to formulate a ordered merge function, this, that takes two sorted lists A and B and merges them into a single sorted list C. So let's say we have been given a two sorted lists A and B. Maybe this has like 10 power 7 elements, this has 10 power 7 elements. We need to merge these two into C, which has 2 into 10 power 7 elements. Something like this. The problem is something like this. uh, so, and uh, like in this chapter, it is discussed that this merge operation is used a lot in distributed computing frameworks like Hadoop, where you have a map reduce operations. So in map, if let's say you have a big problem, in map you map this big problem into, you create smaller sub problems for this big problem and map each sub problem to a piece of hardware, let's say, and make each piece of hardware responsible for solving that smaller sub problem. And once each piece of hardware comes up with a solution for that smaller sub problem, you reduce the results of all the individual hardwares into one single result using a merge operation. So this is where we use the merge operation. This is a sequential merge algorithm. This is straightforward, like this is the merge operation we use in merge sort, so I won't be discussing this. This is just like the logic is, if you have A and B and you want to form C, so you begin with 0 indices, compare this and this, whichever is smaller, you, let's say this is smaller, you copy this to here, increment this, compare this, whichever is smaller, let's say this is smaller, you increment this and this, like put this here. Now you compare this and this, let's say this is smaller, you put this here, increment this and compare this and this in the next iteration, and so on. So this will take like order of, let's, if this has m elements, this has n elements, this will take order of m plus n time, because this has m plus n elements, and for each element we do one comparison of these two elements. Okay, so this will take, the time complexity is order of m plus n. So now we discuss a parallelization approach which uses a corank function. So the corank function is, let's just define a corank function for now and then we'll discuss why we need to use a corank function. So let's say we have been given a k. So in this case, let's say k is equal to 4. So we define k as the rank. Okay, so given, for a given k is called the rank. We intend to find I and j such that I plus j is equal to k, and uh, like this observation. Yeah, for a given k, we intend to find I and j uh, such that this array C from 0 to k minus 1 can be formed from arrays. This can be formed by merging these two arrays. Okay. So, and the answer, and for a given k, we'll have a unique I and j, and the values of I, j are called coranks for k. Okay. Now, the reason we need a corank function is, let's say we uh, remember that the problem is to generate the output array C, right, which contains the uh, merged elements from sorted arrays A and B. So let's say that we map each subsection of the array C. This is the output array C. We map each subsection of the array C to threads in our uh, CUDA hardware. So, for example, if this subsection is belonging to thread 1, next 4 elements to thread 2, next 4 elements to thread 3, and so on. If that is the case, then we can say that we will, for let's say for thread 2, we'll, this is the current k and this is the next k. Okay, so if we have a corank function with us, let's use the corank function as a black box for now. If we have a corank function with us for thread 2, it can call the corank function for uh, okay, this is we are calling this k current and we are calling this k next. Okay, so we are calling corank function for k current will give us I current and j current, and I next, j next would be, we'll get I next, j next from corank k next. Now what this means is, if this is array A, this is array B, um, this is I current, this is I next, this is j current, this is j next. So what this means is thread 2 will be formed by merging elements from this range to this range. Okay, so if we can use corank function as a black box, let's say we have a corank function and we are using corank function as a black box, we know for each thread we know the k current and k next values, because that's the way we are mapping like that's the way we have mapped threads to elements of C, right? So we know k current and k next, and using corank function we'll be able to identify that this thread, like the elements covered by this thread, which are these elements of C, are generated by merging the elements, which elements of A and B, which are these elements and these elements. So now that we know this, we can generate all of these elements. We can generate all of these elements by calling sequential merge function on the let's call this green part as A sub and this green part as B sub. So we do a sequential merge on these two arrays, and let's call this C sub. So we can say C sub is equal to sequential merge of A sub and B sub. Cool. So now that we know why are we defining why corank function is such a big deal, we'll see how we can implement a corank function. And as you can probably guess, what is corank? Corank is um, wait, Corank. Okay, corank is the we need to find a pair of I comma j, and note that since I plus j is equal to k, the degree of freedom for I comma j is essentially 1. If we fix I, j is essentially fixed because k is fixed, and if we know I, j is also fixed. So let's just say we want to find I such that I plus j is equal to k, and for given k, we can generate C, the subarray C 0 to k minus 1 from A 0 to I minus 1 to B, and B 0 to j minus 1. So we can define this problem of finding corank as a binary search problem if you think about it, because if I is 2 less, right, if I is 2 less, um how do I put it, okay, if I is 2 less, the value of j will be higher, right, because I plus j is fixed to k. If I is 2 less, then the bigger values of j, for bigger values of j, b of j would not be in the subarray C from 0 to k minus 1. Whereas if I is too high, then if I is too high, then the later values of AI for bigger i's would not be in C, in the subarray C to 0, in the subarray C 0 to k minus 1. So we need to find this sort of a binary search problem where we need to find an optimal value of I such that the values a to 0, such that the values a to 0, a 0 to I minus 1 and b 0 to j minus 1, these values all lie in this array, and the number of values like I and j is equal to number of values k. Okay, now that we have this intuition, we look at how the corank function is implemented. This is just a binary search function where this is the binary search condition, and this condition means uh, ai minus 1 is greater than bj. That is, we should move the partition of I towards the left, and in this condition it means we should move the partition of I in a towards right. So let's just do a sample code run. Let's say we are at k is equal to 3, and we need to find the corank of k is equal to 3, which means we need to find values of I comma j such that a, this is subarray a, this is subarray b, and this is the merge subarray c. Okay, and we need to find values of I comma j such that a 0 to I minus 1 and b 0 to j minus 1 would give c 0 to k minus 1. Find corank I comma j such that this and I plus j is equal to k. Okay, so according to this, we initialize I to I initialize I to 3 and j to k minus I. Okay, so I to 3 and j to 0. So we are expecting all, this means all elements in C, like in this subarray, come from A. That is the initial condition, which we see is not true of uh, because of this condition, because of this condition, right? So because a I minus 1, that is this 8, is greater than bj. This means that while merging, there is no way that uh, like C is formed by merging subarrays A and B, right? So while C was being formed, there is no way that this element was not taken and this element was taken, because then this just this, like if this happened, then the merge is not correct. Then the merge did not uh, then after merging, C is not in a sorted order. So this tells us that I, the partition for I, should be shifted. So we, from I is equal to 3, we do a correction in the binary search and move I is equal to, from I is equal to 3 to I is equal to 1, and j from 0 to j is equal to 2. Okay, now we see that uh, so now the expectation is 1 and 7 comma 10 form 177, this subarray, which is not correct, right? And the reason it is not correct is because there is no way uh, during the merging this 7 was not taken and this 10 was taken, right? So this tells us that we should move I towards the right. So from I is equal to 1, we move I is equal to 2 and j is equal to 1. Now we see that this and this are supposed to generate this, which is indeed the case. So we break and we see that for k is equal to 3, the corank values are I is equal to 2 and j is equal to 1. Okay, so now that we have this corank, we have understood this corank function, how it works. We see how a merge kernel works. So let's say this is the entire C array that we wish to generate. We know that it will have m plus n elements, where A has m elements and B has n elements. And each, we map all the m plus n elements into blocks, and each block, and within a block, we make each thread responsible for a certain range of elements. So for example, each thread we say is responsible for 3 elements. So for each thread we find, so let's say for this thread 1, we find what is the k uh, value here, and what is the sorry, we find the corank values for this we call this k current, and corank values for this we call this k next. And once we have the corank values, we know the we once we have the corank values, I current, I next, and j current, j next, we know that these three values come from A, I current to I next, and B, j current to j next. So we need to merge these two to get these three elements, and we can just do a sequential merge to get this. Okay. So now that we have discussed this, the problem with the current approach is that the memory accesses to global memory by the corank function are uncoalesced. And why is that the reason? Okay, so every time we are, since everything is in the global memory, every time we do a binary search, we are like jumping between elements, right? So consecutive threads do not access consecutive locations in the memory. So we are doing uncoalesced accesses to global memory. So we would want to avoid that. And obviously, the first thing that comes to mind is we could use probably shared memory. And the way we do that is, remember we were dividing the array C into blocks, and each block, uh, like within each block, we were mapping elements of C. Sorry, so C, each block covers certain elements of C, right? Certain range of elements. So, for example, this first block contains these elements, and within each block, we know that each thread contains covers certain range of elements. So, for example, thread zero covers these elements. So, rather than finding co-ranks of each thread independently, we would find co-ranks of each block. So, let's say, for example, uh, we would assign the job of finding co-rank of each block to the thread ID 0 of that block. And once the thread ID 0 finds the co-rank for that block, so uh, let's say for block 0, these are the co-ranks. For block 1, these are the co-ranks. For block 2, these are the co-ranks, right? So once this has been identified, we know that for block 0, from uh, corangs I1 J1, we'll call it I, let's say, we'll just call it I1 J1. This is I2 J2. We know that uh, like blocks B0, okay, oh yeah. So we know that block B0, the elements of C covered by block 0 can be generated from the elements of A in the range I1, A in the range I1 to I2 minus 1, and B J1 to J2 minus 1. So we'll just make sure that all of these threads in this block load these elements of A and B into shared memory first, using from global memory to shared memory using coalesced access pattern. And then when we are doing binary search, we use shared memory, uh, like we access shared memory to do binary search, because uh, even though the accesses to shared memory won't be coalesced, the penalty for non-coalesced accesses to shared memory is much lesser than the penalty for non-coalesced accesses to global memory. Okay, and one thing to note here is that we'll have to we can't just load the entire, since shared memory is a limited resource, so we cannot load the entire um, entire this array and this array into shared memory. We'll have to, let's say if we put a cap of, we want to use x shared 2x shared memory for A and x shared memory for B, that is 2x total shared memory. We'll do this in iterations. So in the first iteration, we'll load x and x into shared memory for A and B. In the second iteration, again x and x, till the time we are able to load all the elements, like all these elements and all these elements. Okay, so the steps are, for let's say we are in block 0. Okay, so for block 0 in C, identify the block ranges in A and B. And the way we do this is using corank functions for this and this. Okay, so once we have identified this, the ranges, so the range is this and this. For iteration 0, we for iteration 0, we wish to populate the first x elements in block 0 in C. So we load the first x elements of A and first x elements of B into shared memory, right? And then uh, once we have loaded it into shared memory, we do a once we have loaded it into shared memory, once we have loaded into shared memory, we just call the corank function for the for these shared memory blocks, and then do a sequential merge. So we do this for every iteration. So let's look at the code now. So in part 1, we are identifying block level output and input subarrays. So as we said, for let's say for we are at block B1, we'll find the current and next, k current, k next, and according to that we'll find these indices which correspond to the indices in A and B, which when the ranges of which when merged uh, would form these elements in C. Okay, and the part 2 is loading elements of from A and B into shared memory. And we do this in iterations, right? Because shared memory is a limited resource, and in every iteration we load x elements from A and x elements from B into shared memory. So this is what we are doing here, and then we sync to make sure everything is loaded into shared memory properly. And in part 3, we for the current, okay, so now after part 2 everything is loaded into shared memory. In part 3 we just do like in the non-tiled version, what we did, we do something very similar to that. So for every thread, we know the range of locations it is responsible for, range of values it is responsible for. So we find the corank for each thread. We find the bound using corank function, and then call a sub sequential merge to formulate the. So what I mean by this is, if this is the block, within the block there are various threads. So for let's say for this thread, we know the bounds, like these bounds, using coranks this and corank this. So using these two coranks we can get the ranges of A, that is A I1 to I2 minus 1 maybe, and B I J1 to J2 minus 1, do a sequential merge and populate this part of the subarray of the current block. Okay, and this is the current thread. So all threads merge their individual subarrays in parallel. Yeah, this is actually a very complicated topic. Very complicated to explain and also to make yourself explain. Yeah, and the problem with this is, if you see, uh, every time you load x elements from A and x elements into from B into shared memory, you are using 2x shared memory to, but from this 2x in each iteration, you are populating x elements in array C. But for populating x elements in C, you need to load 2x elements into shared memory. So you could see that in each iteration, only x elements are being used, whereas x elements are being wasted. So here is the drawback where x elements are being wasted, and in the next iteration we'll be loading these x elements again. So the way we avoid this is using a circular buffer merge kernel, where essentially the idea is in the previous approach we just had an assumption that if these are shared memories, like this is A shared, this is B shared, this is A shared, this is B shared. So for each iteration, the shared memory starts from here. This was the assumption, and that is why if like these were being used and this was being used in first iteration, in the second iteration we were having to like rewrite values again, and in the second iteration maybe this was being used and this was being used. This is iteration 1, this is iteration 2. But it would have been more it would be more optimal if we can do something like this. This is the first iteration where we say A start is this, B start is this, and in the second iteration we just specify that A start is here, B start is here, and we populate the new elements. So let's say the new elements are this and this, and A start is here and B start is here. So it can just, rather than reloading elements, it can just reuse this. So yeah, this is the major idea without getting into too much details. Yeah, and they discuss about this more, which is a little complicated. That's it for the merge operation, and once we understand the merge operation, we can now move on to understanding how sorting algorithms work in on GPUs. That is parallel sorting algorithms. We'll discuss about parallel sorting algorithms next.